Thank you very much. I would like to thank the organizer for this very nice meeting. So I'd like to present you a work that is made with many people, Sophie Ricci, Richard Ménard, Marc Bocquet, Virtual, and Ronan Fablé for the neural network part. So what is the motivation of this talk? Whoops. Okay. So if you want to use Kalman filter, you know that Kalman filter is a very simple way to filter the information. It relies on simple linear algebra equations. But the problem is that this dynamics, thank you very much. This filter is very costly, especially for forecasting the information from a given time to another time, and also in the update of the information during the analysis time. So when you merge observation from the system and the information from the past. So a tricky way to solve this problem was to introduce the ensemble method. But the ensemble method, so ensemble method can be considered as a way to approximate huge covariance matrix here by some estimation from an ensemble. So it's a way to approximate a matrix, okay? And by this way, with propagation of each member, you estimate the propagation of the information, and then during the update with the observation, you mimic what assimilation does. So another way, possible way to represent the time evolution of the information is, in place of using an ensemble to approximate a covariance matrix, you can use a covariance model. So covariance models are really usual when you consider variational data assimilation system, for instance. And so if you have a covariance model that relies on some parameters, for instance, the variance. Variance can be one of the parameters of your covariance model. Then if you are able to predict equation, to provide equations that predict the time evolution of your parameters from a given time to the next time, and also equations that explain you how to update the information considering observations, then you are able to reproduce all the forecast and the analysis cycle of the Kalman filter. So the problem, of course, is then to, given a covariance model, what are the equations for the analysis, how you can update parameters, and what are the equations for the forecast step? How can I determine equation for my parameters? So in this talk, we focus our attention on the forecast steps. Okay? We have results for the analysis step, but for this talk, we focus the attention on the forecast. So, more precisely, what is the parametric Kalman filter? If you consider a covariance model here, I show you an example of such covariance model. You can build a huge covariance matrix, considering it as a product of linear operator. So one matrix sigma corresponding to the standard deviations, so diagonal matrix formed from the standard deviation. An operator L that can be, so it is a linear operator that can be, for instance, here a diffusion equation. And so with this covariance model, what are the parameters? You have the variances of the covariance, and you have the diffusion tensor of the diffusion equation. So you have two parameters. And these parameters can be related to the shape of the correlation. For instance, here, you can see that if you consider a Taylor expansion of the correlation, then you have some quantities that are related to the tensor, to the diffusion tensor. So this is an illustration of what such tensor represents. So if you have some correlation function that are elongated with the flow, then this tensor nu here corresponds to the anisotropy of the correlations. And if it's quite isotropic here, you have a tensor that is a magnitude, 2 within the magnitude equal to the identity. So what's our equation for the parametric Kalman filter? So to introduce the equation, I show you on an example. So don't think that this corresponds to the full question, okay? Just an example. And because this is much practical to understand. So if I consider here this very simple dynamics corresponding to the transport of a tracer, for instance, we can introduce the Reynolds decomposition of the fields. So this field is considered as a random field, for instance. So you can always separate this field in two parts, the mean and the error. And you can define the variance from this error as being the expectation of the square. And you can also define the metric tensor that is completely related by some assumption, but anyway, to the diffusion tensor like this. And so if you want to compute dynamics of this, you can use these two definitions and apply a time derivative. So with the commutativity of the expectation with temporal derivative, you will obtain the equation for the variance, like for Reynolds equations. But at the difference of the Reynolds equation here, the second equation here, the second dynamics, is not usual, but anyway. And of course, the problem is to compute this equation. So you can do this by hand, but it's quite complex, quite long. It's not complex, but it is long, and you may introduce some errors. So it's not nice. And you can use a very simple algorithm with multiple states. So you follow these recipes, and at the end, you have the dynamics of the variance and of the matrix. So to use this 4 steps recipes, you have to compute, to design the operator, the expectation operator. And so all these steps can be done by using a computer algebra system, like Maxima, Mathematica, Maple. Here, I prefer to use SymPy because it is in Python. And if I want to test that the equations obtained are right and corresponds to a good approximation of the dynamics of the covariance, I need to do numerical experiment. And if I want to do numerical experiment in Python, it's more friendly for me to have a complex algebra system in Python. So to have an integrated framework, we use SymPy for the complex algebra system and Python for the numerical illustration. So from now, all this is done in Python, okay? So an illustration of the algorithm, if you give to the system, to the software, if you give this equation and press enter, it's magic, you have all these systems that govern the dynamics of the variance and of the anisotropy. Okay? So this system, as you can see, contains many terms. So it is here an illustration in 2D. For 3D, the number of terms increases. But if for this particular case, there is a much more compact way to represent the equation. So this corresponds, so the first equation, you recognize the one you set in the initial condition. So you provide to the software. Except that here, C corresponds to the expectation of C, but it's just a change of notation. When you want to solve this equation, it doesn't matter. So you have the equation provided to the software. You have here the dynamics of the variance that corresponds to conservation of the variance. Okay? The variance is conserved in that case. And here, the transport of the tensor, of the anisotropy, with some deformation due to the shear. Okay? So the tensor will move, will change because of the gradient of the velocity. Okay, so an illustration with a numerical demonstration. So considering a given velocity field, so fixed here. Just an illustration, I remind you. So here, an illustration. So you start from a given concentration of your tracer, and with the advection by the flow, this pattern will move into this one. So to verify that the equation we show corresponds to what should be reproduced by the nature, if the nature is given by the dynamic of the tracer, you can use an ensemble method to estimate. So you sample, you consider a given covariance matrix as an initial condition. Here, this corresponds to a correlation matrix. I said the variance equal to 1. But if I want to check, to verify that this equation is good, I need to sample it, okay, to create some samples. So this introduces some sampling error. Okay, so this is, for instance, an example of variance field estimated from a large ensemble. Here in red, this corresponds to the variance that is fixed, and this is provided to the algorithm, to the equation I showed you before. And the time evolution of the ensemble is reproduced here. So actually, the evolution of the signal is close to 1. It is not exactly to 1 because of the sampling noise. But for the parametric Kalman filter equation, so the dynamics of the variance, the solution, the numerical solution of this reproduce the conservations of the variance. For the tensor, so I don't show here the initial condition, but it corresponds to circles, so whole circles in every point. And here, this corresponds to the solution of the evolution of the system for the tensor after a certain time window. So at the end of the time window, we have this kind of patterns. So with orientation of each ellipses along the flow, which exactly corresponds to what is provided by a large ensemble. So this is an illustration to show you that this approach, by only solving very simple partial differential equation, is able, for this case, to reproduce the dynamics of the covariance matrix, okay? But without solving M, PA, M transpose. Okay? So now we can test it on much more complex dynamics. So the Burger equation with a nonlinear terms and a diffusion terms. So this is a very interesting equation because it looks like advection in meteorology, for instance, or oceanography. So starting from a very smooth signal, this equation will create a shock, some kind of front, okay, after a certain time. And this front is regularized by the diffusion. So the presence of higher order derivative will introduce unknown quantity in this process. And these unknown quantity are of this form. And so the equation that you will obtain from the software will introduce this kind of terms that can be related always, it's very nice, to the correlation functions, to the Taylor expansion of the correlation function, and especially this kind of terms. So this will be used, for instance, to close the system. So given the Burger equation and pressing enter, you have this set of equations. So the first one corresponds to the Burger equation plus a term that corresponds to the retroaction of the fluctuation on the mean. So this equation is not exactly the Burger equation. It corresponds to the equation for the expectation. Okay? The next one corresponds to the dynamics of the variance, okay, with a term of transport here. Recognize the term associated to the advection. A source term corresponding to an uncertainty related to the gradient of the flow, and other terms related to the diffusion. The last equation corresponds to the dynamics of the diffusion tensor. Okay, in that case, in 1D, it corresponds to only a single scalar field. So with the transport here, with the deformation of the flow here, and other terms related to the diffusion process. So this system shows some coupling between the three fields. So the mean field, the diffusion here interact with the variance, and for the diffusion, the variance will act on the diffusion. So it's a quite complex field with, as announced before, with some unknown terms. Okay, so I won't detail how we can close the system, but for this we have proposed a closure which takes this form. Okay, it's not very simple, but we have a paper that describes how we close this system. So as an illustration, if we start from a perturbed initial condition with a magnitude that depends on depends on the standard deviations, that here corresponds to very small noise, so it corresponds to the tangent liner dynamics, and here to very large noise corresponding to a non-linear situation, a huge non-linear situation. Then you can appreciate the attenuation of the signal. That is a way to understand the coupling between the variance and the diffusion that were shown before in the equation. Even if it's this dynamics corresponds to the dynamics of a perturbation. The system before corresponds to the dynamics of the parameter. Okay, so solving these equations, considering an initial condition where the signal is the smooth one and with a variance equal to 1, we have, in the case where the noise is very low, this solution. So you recognize here the solution of the unperturbed systems. This is normal because at the tangent liner regime, you know that the average of an ensemble corresponds exactly to the forecast of the average. Okay. But if you introduce larger noise, then you can see that the average of the system may be different from the non-linear trajectory of reference. Okay, so part of this information is reproduced by solving only these simple three equations. Okay, so concerning the variance, okay, so starting from a uniform variance, at the beginning, the variance is damped because of the diffusion, but you have some source term, like for in turbulence, for instance, associated to the formation of a front. So where there is a gradient, you have an increase of the variance. And solving this equation and compared to the ensemble, so the ensemble is not used, okay, for solving this equation. It is just used to verify that the prediction of this system is in accordance with what we should obtain from an ensemble Kalman filter for the forecast steps. Okay. So you can see that there is a good accordance between the solution of the system of the parametric Kalman filter and what is done by the ensemble. And if the magnitude of the noise is very high, there are some difference between the solution of the system and what is provided by the ensemble, but you see that for this situation, it's not so bad. Okay. So you can see now what's happened for the diffusion. So in place to look at the diffusion, which is not very simple quantity, it's the square of a length divided by time. So you can look at some length scale, which is just a length, okay, and look at the evolution of these parameters. So just the square root of the diffusion. And starting from an homogeneous formulation, you can see that the length will increase. This is due to the diffusion, except near the formation of the front, where you can see here some oscillations. So if you look at what is given from the ensemble, you would suspect an error in the diagnosis. It's very strange to see this oscillation. But if you solve this equation, this oscillation appears. So it means that there's some information that justifies this kind of very small details, and this information is captured by the dynamics. So it's nice. Of course, when the magnitude of the noise is very large, you find some correspondence between what is given by the ensemble, but you see that it is not so good as for the tangent liner case. Okay. So from this software, we are able to, given an equation, providing the set of PDE describing the time evolution of a covariance. One question should be, well, here we are close the system. And it's not obvious, and you have the choice of the closure, and some of the closure may be not so appropriate. And we would like to learn this kind of terms. So to doing this, we have designed a software able to transform a given partial differential equations, so evolution equation, into a neural network. Okay? And this is here an example. Again, just an example. Consider your favorite diffusion equation. Convert this equation into a neural network and compute with it like your classical numerical model. So starting from Dirac, solving this equation with the neural network, you obtain this pattern. Okay, if this kind of equation is too simple for you, don't forget that, well, actually, in this equation, we have terms that look like an advection, and terms that look like a classical diffusion. So it's not so simple. Well, okay, it's just an example, but we do that for the system provided by the parametric Kalman filter equation or strategy. And so, given this set of equations, we can generate a neural network that solves this system, okay? And since we are in the world of machine learning, we can specify the form or try to estimate the form of this unknown quantity. So, just for an illustration here, okay? We suppose that this term looks like the one we have given as a closure, just an illustration. But in this situation, we don't know what are the weights of these terms, okay? And try to see if we are able to learn this term. Well, the answer is yes, we are able to learn this term. So to learn this term, we have generate numerous ensemble forecasting in order to estimate what is ensemble mean, what is the variance, and what is the diffusion tensor. So this corresponds to our training data. And here you have the estimation of the parameter. Okay. So at the top you have the solution of the dynamics as resolved from the trained neural network. And at the bottom, this one corresponding to a huge ensemble. So you consider a very large ensemble. And so if the training is correct, you should see that the two, the top and the bottom, are equal. Well, it is not exactly equal because of the sampling noise and because the closure we have introduced may not be exactly what should be the nature, but anyway, you see that with this training, we are able to reproduce a large part of the signal. Compared with the theoretical closure introduced before, so the weights are not exactly the same, but that's not a problem. The closure we have introduced to close the problem was arbitrary, and there is no reason why this term should be the good one, okay? But in this situation, it's not so bad, and fortunately, this was what we have seen before. So as a conclusion, the parametric Kalman filter is a way to reproduce the dynamics of a covariance matrix but at a very low cost with usual equations, except that some unknown quantity may appear. But here we have shown you that this kind of quantity might be learned from the data. The problem is to design the dynamics of the parameters, but the software is here to helping this task. And thanks to the code generation, which translate any evolution equation, partial differential equation into a neural network, you have an integrated framework to compute the dynamics and train the dynamics. Okay? And I would like to say that if this parametric Kalman filter is a way to solve, it's a pragmatic way to solve the evolution equation of the Kalman filter, well, since it seems to work, at least for this situation, and it is exact for transport equation, it seems to work, it can be seen as a tool for understanding the dynamics of the covariance, but in a way much more friendly than linear algebra. MPA, M transpose is not so simple than partial differential equation. Okay. That's all. Thank you very much.
Time for a question or two.
Olivier, thank you very much for this very interesting talk. I didn't catch the point. How did you choose the different terms in your closure there? Not the coefficients, but the different terms of the closure.
Okay, this has not been detailed in the presentation. There is an article that details this how we choose the closure. It is rated from. Okay, sorry. Okay, this term, okay, can be rated to the correlation function, and actually here this term corresponds to the expectation of the square of the second order derivative of epsilon. And for the particular case where your correlation is Gaussian, so we have some assumption here, and locally Gaussian, then this term should be equal to this one here. This one is exact, okay? And so it's a way to close the system. And if you replace the metric by the diffusion, then you obtain these equations.
Okay, thank you.
Okay.
I'm not sure what the second microphone went.
Okay, Olivier, thank you. It was a very interesting talk. I was just wondering, obviously you showed you were successful in predicting the evolution of the first and second moments of the errors of the Burger's equation, but do you envisage a real-world application for this at this stage?
Yes, and to envisage such real-world application, we need some tools. And first of all, we need a software that is able to design the equation. That's what. And since this work has been done, now we can tackle much more complex dynamics.
I have just a small comment. I don't know much about the stochastic Burger's equation, but in the case, the deterministic, even with forcing, it's known that the dynamics is trivial. It always goes to steady state. So probably one has to embark on something, even one-dimensional, but with interesting dynamics, so that basically to see the machine is working. If in the deterministic everything goes to steady state, it's boring dynamics, and therefore probably sometimes no surprise. To make the point, probably I suggest that you should look to something even one-dimensional like Kuramoto-Shevashinsky or something like that, or some non-local version of the one-dimensional Burger's equation, the non-locality to mimic the pressure or something like that. There are models of that type which have interesting dynamics. That's my suggestion.
Well, as I said to Massimo here, this is just an example, and we want to tackle much more complex situation. But okay, so here, this simulation corresponds to the integration of a time window which mimics what we are doing in data simulation. So yes, we are not interested by the limit, the ergodicity of the system, for instance, the limit distributions, if it was a question, a part of it.
Okay, any other questions? All right, if not, let's thank Olivier one more time.
Thank you.